So today we're gonna talk about partial derivatives. Um, Last time we talked about continuity along with the properties. Before we talk about partial derivatives, let's do a couple of examples here, okay? Let's talk about continuity of a function with a few examples. Function of two variables. Continuous at a single point means the following. It means the limit as xy approaches x naught y naught. It means the limit equal to the function's value at that point. And notice this is identical to the continuity for a single variable function. So now I'll provide some similar examples. So here when x is not 0, we have a function sine 1 over x. We multiply this with x plus y. So if you picture this, when x and y approaches 0, 0, okay, when x, y approaches 0, 0, this term goes to 0, and this term, well, it's less than 1. So we're feeling that the limit of this might be 0. And the function is defined to be always 0 when x is 0. So that is along the y-axis. Whenever x value is 0, the function's value is always 0. If x is not 0, it's defined by this. The question is this function continuous at the origin? So here we suspect that it is, because this guy the limit appears to be 0, which matches with the function's value at 0, 0. But we need to prove it. When x is not 0, we take a look at the function's value. I take the absolute value of it. It's pretty easy to check that this is bounded by x plus y's absolute value, because sine absolute value is less than 1. And when x is 0, f of xy is always 0. So this one is always less or equal to x plus y's absolute value. Around 0, 0. When x is not 0, it's bounded by x plus y. When x is 0, it is 0. That's also less or equal to what? Say x plus y's absolute value, where x is 0. Where x is 0. And it's easy to see that the limit of x plus y, the limit of this is actually 0. So similarly, we have the squeeze theorem here. This y goes to 0, and this one is bounded by x plus y absolute value. So we claim the limit of the function at the origin is also 0, okay? The squeeze theorem. Well, which matches with the function's value 0, 0. f0, 0 because x0 is always 0. Thus, it is continuous. So here, to figure out this limit here, we use the squeeze theorem and to get the limit. Next example. So for this one, we can try to figure out the limit. Sorry, I didn't finish the question here. Is it continuous at, once again, the origin? So for this one here, you can try different path to 0, 0. You will find out that this guy along different path will always goes to 0. Will always goes to 0. But the thing is, how do we prove it? So we want to prove the limit is actually 0, okay? So here we have a arbitrary epsilon. Need to find the delta so that the difference between the function's value and the proposed limit, which is 0, is less than epsilon whenever, well, the norm, okay, whenever the distance from the point. So here you have the origin, you have a random point, you are trying to let xy approach 0, 0. So whenever that distance, which we're going to use the Euclidean norm, so just the normal distance function here, whenever this is less than delta. Okay? This one, we're going to proceed to take the x value. We notice y squared and all those terms are positive except, x apps value, except the x here. So we simply take its apps value, leave everything else alone. So we need this to be less than epsilon. So now let's see if we can play with the inequality and make this work. The y squared on the top is obviously less or equal to x squared plus y squared. So this is less or equal to just 4x apps value. Alright, because this fraction here is less than 1. But then somehow I need to connect this with square root of x squared plus y squared. 4 stays here. X apps value obviously is the same as square root of x squared. Okay, that's identical. So if I add a y squared, this term will be less than this. And I need this less than epsilon. So this will be true. if we pick delta to be something you can think about really quick, delta will be what? Well, epsilon for 4, okay? Epsilon for 4. Thus the limit at the origin, it is 0, okay? It's 0, which is identical to the function's value 0, 0. So we have what? Continuity, okay? Continuity. Um, now we're gonna start the topic of differentiability. Differentiability of function of two variables. Before we talk about differentiability, now here we are not just talking about partial derivatives. We are talking about what do you mean by say a function of two variables is differentiable. Before we do that, let's try to take a look at single variable function. For a single variable function, f of x, if the derivative exists, then f has to be continuous. So if f exists, okay, if the partial derivative exists, sure, that's in single variable function. That means this guy, is differentiable at that point. But that also implies f has to be continuous at that point. For function of two variables, however, this is a different story. For function of two variables, let me just bring up this this difference here. It can have partial derivatives. Partial derivatives with respect to both those two variables, but f may not be continuous. So that's a huge difference here. That's a huge difference here. And it's hard for us to picture this. Let me present an example. Notice here we're not talking about differentiability right now. Okay, I'm just talking about partial derivatives, which we assumed something we learned in Calc 3. So I'll give you a very simple example. So this function is defined to be 0 when none of x and y is 0. If one of them is 0, for example, along the y-axis or along the x-axis, the function's value is 1. Is 1. Everywhere else is 0. Okay, everywhere else is 0. You have the x-axis, you have the y-axis, and this is your z-axis, which is f of xy. So basically, this function equal to 1 when x is 0, in other words, along the y-axis. So you got this horizontal line. It is also 1 when y is 0, that is along the x-axis. Alright, so you got two horizontal lines there. Everywhere else, okay, So away from x-axis or y-axis, they're all zeros. Okay, they're all zeros. So they're all zeros. So this is essentially almost just the xy plane uh, combined with those two horizontal line that's up there. All right. So that's the graph for this function. Two horizontal lines on the top, and then the xy plane where you get rid of the x-axis and y-axis, because along those two axes they are going to be one. So this is a simple function. Uh, so to talk about continuity, okay? So to talk about continuity, you have to figure out the limit when xy approaches 0, 0. Okay, so here we're talking about continuity at the origin. So we try to find this. Similar to what we talked about before, you will find out that this limit does not exist by, well, once again, pick different path, okay? This limit does not exist. And that's something you guys need to think about, okay? Why this limit does not exist. Like I said, try different path and see what happened, okay, folks? So, so essentially, if you pick the path to be, say, along the y-axis or x-axis, when xy approaches 0, 0 along the x-axis or y-axis, the function's value is always 1. So that limit is always 1. Anywhere else, okay, if you pick x and y approaches the origin from any different path, keep in mind all those y values, all those functions value, they're always 0. So the limit will be 0. And that's why the limit does not exist. Think about that. However, the function's value is 0, 0, okay? That is when x 0, y is also 0. It is actually, it is 1, okay? It's 1. And they don't match. And that's why we say this guy not continuous at the origin. However, I want to show you that this function here that we presented, it'll have partial derivatives at the origin. So let's try to recall how partial derivatives are found. So to evaluate partial derivative, say with respect to x and with respect to y is the same at 0, 0. Here's what we do. We will fix the y value to be 0. We'll let h goes to 0. We'll fix the y value to be 0, okay? So we try to figure out the function's value at h 0 minus the function's value is 0, 0 and divide by h. And then let h goes to 0. This is how we calculate the partial derivative of the origin. fh0, because the y value is 0, so the function's value here is 1. f0, 0, that is also 1. Okay, that is also 1. Divide by h. So this is actually constant 1. So the partial derivative with respect to x at the origin actually exists, and it is 0. Partial derivative with respect to y at the origin, the same story, is also 0. So for this function of two variables, partial derivatives exist, but the function is not even what? It is not even continuous. It is not even continuous. So that's a huge difference. Now let's practice a little bit more. How do we calculate partial derivative? All right, just want to refresh your memory. Now keep in mind, partial derivatives is not the same as differentiability. Okay, that's what we're trying to say here. But let's practice on how do we calculate partial derivatives. This function right here, it simply means at the origin, that is when both x and y are 0. When both x and y are 0. At the origin, the function's value is defined to be 0. Anywhere else is defined to be this exponential part, e to the power of -1 over x squared plus y squared. Our goal here is to calculate partial derivatives. Now let's recall how this is done, okay? Obviously, away from the origin, we are using this single formula here. Calculating partial derivatives, it's just a matter of treating the other variable like a constant. All right, so that part is kind of straightforward. When x and y is away from the origin, this condition is equivalent to this. X squared plus y squared is not 0 because they're identical. So away from the origin, the partial derivative with respect to x is always, do a quick chain rule here, okay? Do a quick chain rule here. Times by, you try to differentiate this guy with respect to x. All right? So there's a negative sign in the front. We're going to square the denominator. Differentiate the top, you get a 0. Minus the top unchanged. Differentiate the bottom with respect to x, you get 2x. All right? Because y is being treated as a constant, that's why we differentiate this part, you get a 0. So it's just 2x. Minus minus is positive. We put this in the front. So if you're not familiar with this, you can practice this real quick, okay? Once again, treat y like a fixed number, say 1 or 5. So when x and y is away from the origin, this formula is easy to figure out. The question is, how do we calculate the partial derivative with respect to x at, say, the origin? So in this case here, once again, we're going to fix y value to be 0. We're going to give x a little bit change and take that change goes to 0. So here's how the partial derivative is defined. Minus the function's value 0, 0. And we give x a little bit change from 0. So it's f of h, 0. And notice the y value is being kept at 0. And then divide by that little change h. And take h goes to 0. So that's how it's calculated. F of h 0, okay? The y is 0. You're going to use this formula here. It's e to this power. F of 0 is 0, 0, okay? It's 0 divided by h. And you can easily figure out this limit turns out to be, well, 0. So the partial derivative with respect to x at the origin is 0. All right. I just realized that probably not everyone is familiar with how the partial derivatives are defined. So let me clarify that a little bit before I talk about differentiability, okay? Partial derivatives. Let me remind you how the partial derivatives are calculated. Partial derivative with respect to x at a specific given point is you do a difference quotient here. You will, because it's partial derivative with respect to x, so you're gonna keep the y value at always at y naught, and give x value a little bit change. Okay, so we're gonna change it from x naught to x naught plus h. All right, so that's the change in the function's value. Divide by h and let h goes to 0. So that's how you calculate partial derivative with respect to x. Partial derivative with respect to y. Same way, but this time you're gonna leave x alone. You give y value a little bit change h, and then divide by h. So that's how that is calculated. Couple of quick examples for partial derivatives. To do partial derivatives, normally if you have a single formula like this guy here, to do partial derivatives, you will simply just treat the other variable like a constant. Differentiate x squared, get 2x. Differentiate 3xy, where y is being treated as a constant, you get 3y. Differentiate y, where y is being treated as a constant, you get a 0. So those two terms give you 0. So that's partial derivative with respect to x. Partial derivative with respect to y. Well, this term treated as a constant, you get a 0. So you get a 3x, okay, 3x. Followed by the derivative y is 1, okay, it's 1. And one last example is this one right here. So let's think about what is the partial derivative with respect to x, and then what is the partial derivative with respect to, g here, g, with respect to y. So I want you guys to maybe pause here for a minute and actually work this out. Okay, pause here for a minute and work this out, and then I'll tell you the answer. Okay, so always keep the other variable as a constant. Apply the right rules. Okay, this one, when I try to differentiate with respect to x here, I left the y alone because it's the product here, and then I apply a quick chain rule for this guy. Okay, sine going to cosine, and xy, I apply the chain rule, get a constant y on the outside. And then to differentiate with respect to y, I did the product rule. Okay, because it's y times by this, I did a product rule. The derivative of y is 1, so that's 1 here. Leave the second component alone. And then another quick chain rule back here. All right. So make sure you double check this. And that's how you calculate partial derivatives. So based on what we just talked about, for function of two variables, even when partial derivative exists, the function may not even be continuous. So forget about differentiability. So that's a huge, huge difference. In my next video, so this is about half an hour long, in our next video, we'll start talking about the meaning of differentiability, okay?